Hello everyone, myself Pushpalata, Assistant Professor, Department of Electronics and Communication Engineering, SJBIT. Today we are going to discuss about Module 2 chapter contents. Module 2 is about 8051 microcontroller instruction set. Basically the 8051 architecture, it has wide or rich instruction set which allows all those computations like arithmetic and logical operations. So in order to perform the arithmetic and logical operations or computations, the CPU basically needs the access data from both internal and external memory, and basically after taking the data, it processes the data and gives back the result. So the CPU, therefore, it uses variety of instructions in order to carry out these operations. Now we are going to discuss all these operations or the instruction set in the coming slide. In 8051, we have access to the memory in wide varieties of ways, and the CPU which access the data in these ways, we call it as addressing modes. And as we can see that there are a lot of addressing modes like immediate, register, direct, register indirect, external direct. So these are some of the addressing modes or the different types of addressing modes which are listed as, and there are various instructions which operate on some of the special function registers like also external memory, code memory. So these makes use of various addressing modes. Now the instruction to be executed, right? So in order to execute an instruction, we need a specific time, what we call it as instruction cycle time. Right, so this instruction cycle time, it varies according to the length of the instruction, and here the instructions that differ with respect to the internal memory, okay, they are quite faster than when compared to that of the access to the external memory. Okay, so accordingly the CPU uses various addressing modes in order to access the data from both external and internal memory. Okay, so we are going to discuss all these addressing modes one by one. To begin with, we have the first addressing mode, that is immediate addressing mode. In case of immediate addressing mode, here the type of instruction where the value we are going to use, the value is a constant value, okay, constant which follows the opcode in the program memory. That means we have the source operand is a constant. Okay, and the assembler basically denotes this constant value using a symbol called pound sign. Okay, that is, you can call it as hash. Fine, so we can load the information to any registers including the 16-bit DPTR, where the DPTR is split because DPTR is a 16-bit register, and that can be considered as two 8-bit registers like DPH and DPL. Okay, so this is an individual 8-bit registers which we can use it instead of 16-bit whenever there is a requirement. Okay, so here as I said, we can load the information to any registers including even the DPTR registers. Uh, Now this is an example. Okay, so here you can see the immediate addressing mode is given with some examples like move a comma hash 25h. So what it is doing, we are loading the content of 25. It is a constant value. It's a immediate value which is presided by hash, right? So the controller or the processor would understand it is a direct value which you are loading to the accumulator. Okay. Similarly, we can load it to any registers like move R4 or R1, R2 to R7 with a value. See, if you mention with H, it is an hexadecimal value. Okay. If you don't mention also, it will take it as an hexadecimal value itself. We can load it to any of the registers, as I said, like A, B, R. Okay. As well, we can also load it to DPTR. See, if we are using the entire DPTR, we have to make use of a 16-bit value. If you are using the 8-bit values, 8-bit location of a DPTR, we can take it as DPL and DPH with 8-bit constant values. Okay. And if at all the value is greater than this, that is FFFF, the DPTR value cannot be loaded. So because it is maximum is 65,535. Okay. So we cannot take up the value, which becomes an illegal value or invalid. The instructions here, what we have seen for the immediate addressing mode. Okay, here it directly takes up the value and loads it to specific location. Now there is some features which are included with the immediate addressing. In case of immediate addressing mode, they are quite fast. Okay, because you are directly loading the value to a particular register. So the features are the immediate addressing is quite very fast, since as I told you, we are loading the immediate value. And also with respect to the immediate addressing mode, we have one more feature that like since we have an immediate value which has to be loaded and that is fixed, okay, at compiler time. Okay, so it is not very flexible. Okay, so I'll just write it. It is not so flexible. And the hash sign, what we are using, it is used to indicate the immediate value, which may be specified in hexadecimal and even binary, or even you can give it as decimal. That means, say for example, I give 25H. Okay, it's hexadecimal. If I don't mention anything, probably it will take it as decimal. And if I want to mention it as like 1011, you can mention it as B. So hexadecimal, binary and decimal, all these things will work for immediate addressing mode. Next we have another addressing mode that is called as register addressing mode. So with respect to the register addressing mode, here we make use of registers to hold the data, and in order to store or manipulate any data, we make use of only the registers. Okay, and the source and destination registers, here it should match in size, because what happens is, say for example, DPTR is a 16-bit but A is only 8-bit, right? So what happens is, when you are loading the data of accumulator to a 16-bit value, the destination location of the registers, it should match. Okay, so and also one more thing you need to go through when you are using a register addressing mode, the movement of the data between the RN registers, that means like R4 to R7, okay, it is invalid. Register to register data movement is not valid in case of 8051 microcontroller. Okay, so let me take you with some examples here. You can see the instructions with respect to the register. We have shown move. Move is a command where it copy the content of one of the location to another location, right? So move is that particular command. And here move A comma R naught. So the actual instruction is it's like opcode, that is move source comma destination comma source. Okay, so what is happening, the contents of R0 is loaded into A, so it is R0 to A. Okay, what happens here in the first instruction, move A comma R0, the content of R0 value, R0 register is taken and loaded in the, or copied to accumulator. Similarly, we have move R2 comma A, where the content of accumulator is taken and loaded into R2. Now already I have some value which I have taken from R0 to R2, That means, say for example, okay, R0 is having 07H, and I have taken this to accumulator. Now accumulator is having 07. Now what I'm doing in the second line, I'm loading that accumulator content to R2. So now R2 is also having 07H. In the next instruction, what I'm doing some arithmetic operations which we will discuss at later stages. But let us have a analysis of this particular program. Add a comma r5. Now a is having value called 05. Okay, but r5 I am not loaded anything, right? So r5 would be by default will be taken as a 0, or some junk value will be there which has to be cleared in the beginning of the program. Now R5 is having 0, if we assume, then accumulator is added with 0, 0 plus 07, it is 07 which is loaded in the result, that is a destination accumulator. Okay, now 07 is there. Similarly, what happens next, I am taking again A with added with R7. Now what happens here, A is having some value like 07 and R7 will be having some values like 00. Again it will add both the contents and store it in the accumulator. Now what I am doing here, move R6 comma A. Whatever the results that is there in the accumulator, I am transferring it to one more register R6. And here you can see that nowhere I am directly transferring from R0 to R2. Can you see this program? Here I am taking the R0 content to accumulator, and from accumulator I am transferring it to R2. But register to register transfer is not allowed in the 8051 microcontroller. So this is about the register addressing mode. Yeah, here we have one more example to say, that is move dptr comma hash 25f5h. Right, so what is happening here, I have just taken up a direct immediate value to the 16-bit register dptr. So now dph is having 25 and dpl is having f5. Now what happens is, you can take up the 8-bit content of the DPTR and load it to some registers like R7 and R6 here. So in the second instruction, what we are doing, we are loading the content of DPL to R7, and in the third instruction, we are loading the DPH content to R6. And we have the next addressing mode, that is called as direct addressing mode. In the direct addressing mode, the operand is specified by an 8-bit address field. Okay, in the instruction, we are going to mention the operand as an 8-bit address field. Now, all the special function registers and including the internal RAM, I can use it for direct addressing method. Okay, so all the internal RAM, okay, and 8-bit registers, whatever we have, okay, so that is special function registers, SFRs, what we call, right? So all these things I can make use of as an address field. And when we talk about the registers, the 4 register banks we have, that is R0 to R3, okay, so R0, R1, R2, R3, and these 4 register banks will occupy the addresses from 00 to 1FH. Okay, so each of these banks are addressed by their names. Okay, so I can take it as R0, R1, R2 up to R7, right? So each bank. So one bank, if I talk, okay, R1, bank 1, then I can take it up to 00 to R0 to R7. Okay, like that we can make use. And uh, with respect to the RAM locations, here we can take up the address location starting from 30 to 7FH, and the entire 128 bytes of RAM can be accessed. Okay, and in contrast to this, we have immediate addressing mode, like where we make use of hash sign in case of immediate addressing mode, but in case of direct addressing mode, we don't make use of this hash sign. Okay. So say for example, I'll give an example to show. Here we have an instruction called as move R0, 40. So you can see here, we have not used any hash symbol here. Hash, if you use it for 40, it becomes an immediate value. Without the hash, it becomes an address field. So it is a memory address location from where the data will be. See, 40H is a memory address location, and the 40H will be having some data like 22. Okay, that 22 will be transferred to the register, destination register R0. Now R0 will contain the value called as 22. Okay, now similarly we have one more instruction, that is move 56 comma a, where the content of accumulator will be stored to the address location of the 56. So 56 is not immediately preceded with hash 0. Okay, so the address field 56 will have the content of the accumulator. So no need to get confused with the immediate addressing mode and the direct addressing mode. And we can make use of SFR, special function registers, and their addresses also here. So you can see some of the examples. Move E0, E0, where the address location is loaded with an immediate value. That is 55 is an immediate value loaded to the address location of E0. Which means that E0 is an address location of a special function register called A. Similarly, the address location of B is 0F0, and which is loaded with the value called as 25. And here also we have, you can make use of instructions something like move A comma R2. So now R2 will be having some content, and that is loaded in the accumulator. Similarly, move B comma R0, which means that we are going to copy the content of R0 to B. So we can directly make use of the address location, or you can point it with the respective register names like A, B, R, something. We are going to discuss about the instructions that are used for stack memory operations, and those stack operations are performed using push and pop opcodes. The push and pop instructions, they use direct addressing method in order to move the data between the direct address and the stack memory. And the stack memory, what we are talking is a internal, it's a part of internal RAM. Okay, so the stack pointer is an 8-bit special function register. Okay, so I'm talking about the stack pointer SP, right? So it is an 8-bit special function register that will be used to always point to the top of the stack. So if I call this is the stack, okay, let me talk about this is the internal RAM, that is a memory, and you have a stack location starting from here. Okay, and the top of the stack, you call it a stack pointer, and every time it will be incremented or decremented based on the operations we are going to conduct. The top of the stack, always the address location of this is 07H. Okay, and since the stack pointer is 8-bit wide, the stack pointer has a range of 00 to FFH. Okay, so we are going to store the value of a register in the stack, and that is accomplished by an instruction called as push add. That means you say, for example, I'll give push some address, give it as A, push A. Okay, A is again 0 E0. If I tell push A, that means like whatever the contents, okay, that it will take it, it will push it to the specific stack pointer location. That means I copy the data from the address location. Here I have taken as an accumulator, and the accumulator content will be taken and it will drop it to the internal RAM address which is contained in the stack pointer. Okay. Next we have to retrieve the data, or to take the data, or to remove the data from the stack pointer. We make use of another instruction called as pop, moving the value from stack to a register. Okay, that is accomplished by pop instruction. We are going to copy the data from the internal RAM address which is contained in the stack pointer to the address which is specified. Now you need to keep in mind, whenever we are making use of a push instruction, every time the stack pointer will be incremented, and whenever we are using the pop instruction, the stack pointer will be decremented. So here we have an example of stack and direct addressing mode, and we are showing the code for pushing the R5 content, okay, and A onto the stack, then pop them back to some other register called R2 and B, okay, where B becomes equal to A now and R2 becomes equal to R5, okay. So initially what we do, we are going to push the content of address location 5 to the stack memory. Now the stack memory, initially it will be having stack pointer pointed the content of 05, okay, address location will be taken. If I call XX something, okay, that value will be loaded in the stack pointer. Next push E0, okay, now what happens, your stack pointer will be incremented and E0 content will be loaded, okay, we'll take it as ZZ. Then whenever we are popping it, okay, so what happens, first it will pop the content then decrement, okay. You need to keep in mind, whenever we are using a push instruction, first it will push the content then increment. Here when we are popping, it will pop the content then decrement. So when we pop it to 0F0, the content where the stack pointer is located will be popped to 0F0, then it will decrement the address location or the stack pointer by 1. Then next pop 02, that means the last content will be loaded to the 02, okay. That means the register which is pointing to R2, okay. 02 is a register R2 and 05 is a register R5, okay. So as I told you, the memory banks will be addressed with R0 to R7. So each and every register banks I can make use. Here 4 register banks, all register banks will start with 00 to 07, that is R0 to R7. So any address location with respect to the register I can make use to move the content or store the content. Here is one more example for push and pop instructions. In this particular thing, we have a mnemonic called move. We are taking an immediate value 30H to the 81H address location. Similarly, we are loading R0 register with ACH, and we will push the content of 00H 00 address location to the stack pointer. Okay, so now stack pointer will point to 31H because the stack pointer will be having the immediate data. Okay, 81 is the address location of the stack pointer. Okay, stack pointer address location is 81H. By default, okay, you are giving an immediate data with 30, right? Now what is happening, it will increment it to 31. Okay, so once it will increment to 31, first it will, the address 31H contains the number which is loaded in the R0, because 00 is pointing to R0, right? So you are pushing the content of 07 that means 0 ACH to R0, that is ACH will be transferred to 31H. Okay, so initially it will be pointing to 81H. Now the stack pointer will jump to the 30H because you are loading the stack pointer with the 30. Now when you push the content of 00, that is R0 location content, 0 AC will transfer to R0 content, that is stack memory location, which is called as 31H, and that is loaded. Next, when I again do the same push operation, it will increment to 32H. Now the stack pointer is pointing to 32H. Then the content of again R0 will be loaded, that is ACH is loaded. Next, what happens is when you pop the content, so stack pointer is pointing to 32 now. Okay, so 32 content will be taken to 01, that is R1. Okay, register. then it will decrement the stack pointer. Okay, so next again we are performing pop ATH. So what happens is uh, your stack pointer is pointing to 31H actually. Now the stack pointer will be equal to 30H. Okay, and port 0 latch now contains the number ACH. Okay, so like this the stack operations are performed and they are analyzed. We have some more instructions in order to perform the data transfer, which are nothing but data exchanges. Here the movement of the data in both the directions between source and the destination addresses will be accomplished by the data exchange instructions. Okay, so we have a command or a mnemonic called as XCH, which is basically used for exchanging the content of two different registers A and R. Okay, so it exchanges the data bytes between A and R. Similarly, address location specified content will be exchanged with the accumulator, and also A comma at RP. So here the exchange of data bytes between the A accumulator and address in the RP. So RP is pointing to say that 30. Okay, so at 30th, at 30 memory location, whatever is the data, okay, so at 30 that will be taken to the accumulator. Okay, and we have something called as XCHD, and this is the command which exchanges the lower order nibble of the accumulator. That means the bits usually from 0 to 3, okay, or 3 to 0, 3 down to 0, which is usually representing an hexadecimal or BCD digit. And with that of internal RAM location, we talk about the location or address location, right? So indirectly it is addressed by R2. Okay, now here XCHD, as I told you, whenever we want to exchange the lower nibble between A and the address in RP, we can make use of XCHD. Okay, lower nibble content will be exchanged, and this instruction is provided with some examples. Okay, you can see here XCH A comma R7, XCH A comma 0F0, XCH. So that means the contents of these things will be exchanged. Okay, and this is an generalized summary of the instruction type what we have seen so far. For data transfer instruction, we have move destination comma source, where it copies the data from the internal RAM source address to the internal RAM destination address. And we have move C A comma source, and this basically move C is an instruction which is used to copy the internal or external program memory byte, okay, from the source to the destination. MoveX is a command which is used for external purpose, that is whenever you want to get the data to or from external RAM, then we make use of MoveX. Okay, next we have seen the stack operations like push and pop. Push source, pop it from the destination, push it from the source, pop it to the destination. Okay, that means copy to the internal RAM stack from the internal RAM source. Next is we have pop destination, which copies the internal RAM stack to the internal RAM destination. And we have exchange instructions where XCH A comma source, which means that we are going to exchange the data between the accumulator and the internal RAM source. And here the lower nibble of the register will be exchanged between the register A and internal RAM.